everyone, welcome to your Precalculus notes. This is the very first video for Precalc, and we are starting on Chapter 0, preparing for Precalculus. There are some things that we need to review from previous math classes, like Algebra 1 and Algebra 2, to help you be successful in Precalc this year. So the first thing we're going to review is operations with pure imaginary numbers and complex numbers. As a reminder, a pure imaginary number is something that has an I in it, so it could be like 4i or 5i or negative 2i, where it's just one term. And a complex number is something where it has a real number part and an imaginary number part. So it could be something like 4 plus 5i or something like that. So first, we're just going to review your concept of the powers of I. And when you learned this in Precalc, you probably only looked at positive powers. Sorry, when you learned this in Algebra 2, I meant to say. But we're going to look at some negative powers here as well. It's nothing too crazy different. Just like you did in the past, if you're trying to find the value of I to the power of n, you're going to divide the power of n by 4. The reason why you're dividing by 4 is because we noticed when we took Algebra 2 that I to the first power is just the square root of negative 1, but then when you raise I to the second power, you get negative 1. I to the third power simplifies to negative I to the fourth power, since that's I squared times I squared, you get positive 1, because negative 1 times negative 1 would give you positive 1. And then what we found out was that I to the fifth is actually the same as I to the first. Similarly, I to the sixth is the same as I squared. I to the seventh was the same as I cubed, and so on and so forth. So since that kept repeating with 4 steps along this circle, that's why we divide the power by 4. And whatever the remainder is, r is the remainder, will tell you what step you're on. So, for example, if the remainder is 1, it's telling you that I to that power is just equal to I to the first. So that's here. With a remainder of 1, whatever you're trying to simplify is the same thing as I to the first. Because, take for example, like I to the fifth. 5 divided by 4 has a remainder of 1, so I to the fifth is the same as I to the first. You could do the same thing for each one. Remainder of 2 is I squared, remainder of 3 is I cubed, remainder of 4 isn't possible because if you're dividing 4 by 4, you get a remainder of 0. So remainder of 0 is I to the fourth. This can also apply to like a fraction. Like if you divide something on your calculator, like if you took 5 divided by 4 on your calculator, it's not going to say remainder of 1. It's going to say 1.25. So if you get a 0.25, that's a remainder of 1 since it's 1/4. Remainder of 0.5 is 2/4, so that's a remainder of 2. Remainder of 3 is the same as 3/4 or 0.75 on the end of your answer. And a remainder of 0 means that your answer is going to be a whole number or an integer. Now this also can work for negative exponents. If your exponent is negative or less than 0, you have similar rules here. It just kind of goes the opposite way around the circle. So a remainder of 1 is the same as a remainder of negative 3. A remainder of 2 is the same as the remainder of negative 2. Remainder of 3 is the same as remainder of negative 1. Remainder of 0 is the same either way. So let's do some examples together here. Alright, so here's our first example. We're trying to simplify I to the power of 53. So in order to simplify that, we're going to take whatever the power is, so 53, and we're going to divide it by 4. You can use your calculator here, or you can use long division. 53 divided by 4 is 13.25. I know that 0.25 is the same as 1/4. So I know that's telling me it was a remainder of 1. With a remainder of 1, I know that I to the 53 is going to be the same as I to the first power, because a remainder of 1 is the same as I to the first. I to the first power is just simply I. So my final answer for this one is just going to be I. I to the 53rd is simplified down to I. We know that's equal to the square root of negative 1, but we're not going to write square root negative 1. We're just going to write I. The next one is an example with a negative power. So we have I to the negative 18. Similarly, you're going to take the power divided by 4. And again, you can do that on your calculator if you want. But keep in mind that you're not going to have a calculator when it comes to this quiz or test for chapter 0. So you'll need to know how to divide 18 by 4 and get that answer. So it's negative 4.5. I know that 0.5 is the same as 1/2, which is the same as 2/4, which means that this is a remainder of negative 2. So with a remainder of negative 2, I can look back at my chart if I want. I know that remainder of negative 2 is the same as a remainder of positive 2. It's the same as I squared. So I squared, I know that's I times I, which gives me negative 1. Because the square root negative 1 times the square root negative 1 will cancel out the square roots and just give me negative 1. All right, there's a couple extra practice problems for you to try on the right side if you want to pause the video, and here are the correct answers for those two. We mentioned this a little bit earlier, but complex numbers, they are always a real part and an imaginary part. It's always going to be in standard form, a plus bi. So the real number part comes first, the imaginary part comes second. If two complex numbers have the same constant and the same imaginary number, but different signs in the middle, those are called complex conjugates. So an example would be like 4 plus 5i and 4 minus 5i. Those are complex conjugates. Those will be useful in a little bit. We're going to work on adding and subtracting complex numbers. It says simplify the following and write the answer in standard form. Adding is really simple because you're just going to combine the real number part. So 5 plus negative 2, which makes 3. And you're going to combine negative 3i plus 4i. That makes 1i. Just like with a variable, you don't write 1x. You're not going to write 1i. You're just going to put I. And then it's already in the right form. The real number comes first. The imaginary comes second. So that's your final answer, 3 plus I. For problem B, it's a little trickier because it's a minus sign in between the two complex numbers. So what you need to do is remember that that subtraction sign distributes. So if you want to rewrite this first, you could drop the parentheses, 10 minus 2i, and then make this minus 14 plus 6i. And now it's similar to problem A, where you just combine the real number part, 10 and negative 14 combine to make negative 4. And then negative 2i and positive 6i combine to make positive 4i. And it's already in the right order. The real number is first, the imaginary number is second. So it's in that order, a plus bi. So it's in standard form. That's your final answer. Here are the correct answers for the extra practice problems. And then we'll move on to the next page, multiplying complex numbers. So when you're multiplying complex numbers, you're going to distribute where necessary. So for example, if we're multiplying this complex number by this complex number, we have to distribute both the real number, the 2, and we have to distribute the imaginary number, the negative 3i. So if you remember from maybe Algebra 1, you might have used the abbreviation FOIL to make sure you got all four terms. That's going to be similar here. So the first times the first, 2 times 7 makes 14. The outside number is multiplied. 2 times negative 4i will give me negative 8i. The inside's negative 3i times 7 is negative 21i. And the last two are negative 3i times negative 4i. That's positive 12i squared. Now it's important to simplify this. You can leave I in your answer, but you can't leave I to a power in your answer. That has to simplify. So I squared, it's always going to be replaced or substitute out with a negative 1. So let's go ahead and simplify this. We have 14. We can go ahead and combine negative 8i and negative 21i to make negative 29i. And then, like I said, we're going to replace I squared with negative 1. Because we know I squared is equal to negative 1. Now we can simplify this even more. 12 times negative 1 makes negative 12. And now we have another real number here. So it needs to combine with the other real number, 14. So 14 and negative 12, those combine to make positive 2. And then we'll put our imaginary number second, minus 29i. That's your final answer for this one. Remember, if you have a binomial squared, it does not work to just distribute an exponent like that if there's a plus sign or a minus sign inside the parentheses. What you have to do is remember that squared means multiply it by itself. So we're going to take 5 plus 2i multiplied by 5 plus 2i, and now it looks like the last problem. We'll distribute the real number. 5 times 5 makes 25. 5 times 2i makes 10i. Then we'll distribute our imaginary number part. So 2i times 5 is 10i again, since multiplication order doesn't matter. And 2i times 2i is 4i squared. Just like on the last problem, our imaginary numbers can combine. 10i plus 10i makes 20i. And again, just like on the last problem, I squared needs to be substituted with a negative 1. So we can simplify this to be 25 plus 20i minus 4. Now we can combine our real numbers. 25 and negative 4 makes 21. So we have 21 plus 20i as our final answer. All right, and there are a couple practice problems here. These are the answers for those two practice problems. And I want you to notice, if you didn't already, that on problem B, you're multiplying complex conjugates. So it's 4 plus 5i multiplied by 4 minus 5i. It's the same thing, except the sign in the middle is the opposite. So notice that when you multiply those, you actually end up with a real number answer. When you multiply complex conjugates, you get a real number. That's going to be important, so write that down next to this problem, because that's going to be helpful in the next few problems when we're trying to get rid of an imaginary number. You have to multiply by its complex conjugate in order to get rid of it. So we'll talk about that more in the next part. When you are trying to divide complex numbers or write the quotients of complex numbers, it is going to be helpful to use the complex conjugate. So when you are rationalizing a complex expression, that's what that's called. It's similar to how you rationalize, because you can't have a square root in a denominator. You also cannot have an I in a denominator, because of the fact that I stands for square root of negative 1. So you can't have I in the denominator because it represents a square root. So what you do is you multiply by the complex conjugate to get rid of the I in the denominator. That goes back to our last problem. When you multiply complex conjugates, it gets rid of the imaginary number, and the result is just a real number. So if you wanted to simplify 1 over 5 plus radical 2, you would have multiplied by its conjugate, 5 minus radical 2. You can't just do that on the bottom. You also have to do that on the top. You can only multiply the same thing on the top and bottom. You can't only do one or the other because this is an expression. So you can't change its value. You can only multiply by 1. We know that multiplying by 1 doesn't change the value. So as long as you do the same thing on the top and bottom, that's multiplying by 1. So it's going to look different, but it's still going to have the same value. If you plugged it into your calculator, the decimal would be the same. So you always change the sign to the opposite. Let's take a look here at example 4. If we're trying to simplify 5 minus 3i divided by 1 minus 2i, you probably want to set it up in a fraction form. You're going to multiply by the complex conjugate of the denominator because you can't have an I in the denominator. So in order to get rid of that I in the denominator, you need to multiply by its conjugate, 1 plus 2i. So notice we just changed the sign in the middle. We can't only multiply by that on the bottom, though. We have to also multiply by it on the top in order to make sure we're only multiplying by a 1. Sometimes I like to call that like a sneaky form of 1. It doesn't really look like 1, but we know this is equal to 1 because it's the same on the top and bottom. So since we're multiplying by 1, we're not changing the value. It's probably helpful to put parentheses here to remind yourself you have to FOIL this out. 5 times 1 on top makes 5. 5 times 2i is going to be 10i. Negative 3i times 1 is negative 3i. Negative 3i times 2i is negative 6i squared. Similarly, on the bottom, you're going to FOIL 1 times 1 is 1. 1 times 2i is 2i. Negative 2i times 1 is negative 2i. So notice we got opposites there. Negative 2i and positive 2i. Multiply together to give you negative 4i squared. All right, let's simplify the top first. We have the real number 5. We have the imaginary numbers 10i and negative 3i. Those together make positive 7i. Then we have minus 6, and we're going to substitute in negative 1 wherever we see I squared. So on the bottom, we're going to do the same thing. We have our real number 1, positive 2i and negative 2i combined to make 0i, so we don't need to write that. They're canceled out. Then we have minus 4, and again, we're plugging in negative 1 for I squared. So on the top, we're going to multiply our negative 6 times our negative 1 to give us positive 6. On the bottom, we're going to multiply negative 4 times negative 1 is positive 4. And then you're going to combine your real numbers, 5 and 6, to make 11. And 1 and 4 to make 5. This would be a good answer, but it did ask us to write the answer in standard form, a plus bi. So we're going to go ahead and split these apart. So it would be 11 over 5 plus 7 over 5i. As long as there's only one term in the denominator, you can split it up like that. Because when you're adding fractions, they just have to have a common denominator, and you combine the numerator. So our final answer is 11/5 plus 7/5 I. Here's a practice problem that looks similar to that with its answer. So you can pause the video and see if you can do that one. And then let's try, well, actually, that's the only one. I don't know why it had an A on it. We were just doing that only one. So, one other thing to watch out for that I didn't mention was that you're going to want to reduce those. So 11 over 5 doesn't reduce, but just watch out and reduce that, both fractions, if necessary. But we didn't have to in either of these problems, so we didn't see that at all, but I just wanted to make you aware that could happen. All right, so hopefully you learned or refreshed your memory on powers of I, adding complex numbers, subtracting complex numbers, multiplying complex numbers, and dividing complex numbers. And you're going to get more practice on that, so let me know if you have any questions. Bye, guys.